So let us start for today. It's a great pleasure for me to introduce Rob Spekkens. He's a frequent visitor to Vienna, a colleague of us in the quantum group and friend. He's one of the leading researchers in the field of quantum foundations and theoretical quantum information. He holds a position of senior faculty position at the Perimeter Institute in Waterloo in Canada. I can just tell a few words about his career history. So he received his PhD from the University of Toronto in the group of John Seip. The title was Aspects of Entanglement. That was from these times, you can put the title of your PhD Aspects of Entanglement. Today it would mean nothing, almost, because the field really multiplied in its context and complexity. From there, after finishing his PhD, he stayed a little bit at the same university, and then he moved to the Perimeter Institute, where he stayed until 2006. When he got the prestigious Royal Society Fellowship and moved to UK to the University of Cambridge, and he stayed there for 2 years until 2008. And afterwards he moved back to Perimeter Institute, the position of a junior faculty, and since 2015 he is a senior faculty member. He is also affiliated to a few other institutions in Waterloo, Institute for Quantum Computing, Department of Physics and Astronomy, and also with the Griffith University in Queensland in Australia. For his work, he received 2007 or 8, okay, thanks, Birkhoff von Neumann Prize from the International Quantum Structure Association. He also won the first prize for the FQXI essay competition in 2012, let's say, something like that. And also was recently invited, and this is a prestigious memorial lecture, Itamar Petovsky Memorial Lecture, organized by Hebrew University, especially for the same type of people is here attending, physicists and philosophers. His work is devoted mostly to the foundations of quantum theory, as I said, and he achieved really few really seminal results, and I just mentioned a few of them. I'm sure he will talk today about that. And one of them is a toy model, which carries his name, and this is a toy model, is a model of a system that mimics quantum theory or mimics quantum mechanical system, but it's not equivalent to quantum mechanical systems. And many properties that we thought of being exclusively quantum mechanically can be actually reproduced by this system, which I repeat is not equivalent to quantum mechanical systems. All his work is, and including the toy model, is in a support of an epistemic view on quantum states, and this is also his title. Then he wrote a very nice, very often cited review of modern physics together with Stephen Bartlett and Terence Rudolph. This is a review of modern physics on super selection rules and resource theory and for quantum reference frames. He also extended the notion of contextuality or contextuality to preparations and transformations. As we remember, the Kochen-Specker argument was initially tailored only for the measurements, but he was first to realize that this can be done also for preparations and transformations. In the recent years, he's more concerned with the problem of causality in quantum theory, and he was proposed also to use the tools from the causal inference that people have developed in other fields, like in medicine, also to quantum mechanical systems. And I welcome him and happy that you are here and giving us a talk.
Thanks very much, Tesla. Can everybody hear me, or do I need a microphone? Is this, yeah? This level's okay? Good. So I also want to thank Flavio for inviting me to give a lecture in this series. It sounds like a fantastic series, and it's always very nice to be back in Vienna. So the lecture today is going to be about how to achieve scientific realism in quantum theory. I'm going to start by saying a few words about what type of realism I think we should strive for in scientific theories, why there's a challenge to achieving that type of realism in quantum theory in particular, and how I think that the way to meet that challenge is to interpret quantum states as describing states of incomplete knowledge rather than states of reality. So because I'm going to be telling you about my own research program on how to interpret quantum theory, and because many disagreements over interpretations often go back to philosophical presuppositions, I'm going to start the talk by laying out some of the philosophical principles that I'm essentially assuming in the research program, so that we can clearly distinguish sort of what's a philosophical disagreement from what just follows from those principles. And then I'm going to try to convince you that if you endorse those principles, then you should interpret the quantum state as a state of knowledge. All right, so let's start with scientific realism. So I want to contrast it with what's sometimes called operationalism or instrumentalism. So if I have a quantum experiment like this one, where you have prepared a pair of particles in some joint state, you send them off to distant labs, and in each lab they're subjected to one of several measurements. So this x is just a variable that labels the outcome of this measurement, and s is a variable that ranges over the possible measurements that can be done, which is just represented by this knob here. Similarly, for t and y over on this system. Then you can just run this experiment many times, prepare many copies of the state, and compute statistics. So for each of the four possible settings, so S and T being 0, 0, 0, 1, 1, 0, 1, 1, I can just compute what the relative frequencies of the four possible outcomes are. So X and Y being 0, 0, 0, 1, 1, 0, 1, 1. And this particular data table I've drawn is something that quantum theory predicts can occur for certain kinds of states and measurements. Okay, so the instrumentalist position is that if a scientific theory generates these sorts of data tables, if it's adequate to tell you what these probabilities should be, then it's doing its job, and a scientific theory doesn't have to do anything more than that. That it's perfectly fine if you've just generated that data. So I want to start by saying why I think that's not adequate. And the way I like to do it is by highlighting a paradox from classical statistics called Simpson's paradox. So let me first tell you what Simpson's paradox is. So the idea is you have a population of people who have some condition, and some fraction of that population has taken a drug, and you compute what fraction of those people have recovered from this condition. And you compare it to the fraction that recovered among those who didn't take the drug. And suppose you find that the conditional probability of recovery is higher among those who took the drug. So that suggests that maybe the drug's effective for this condition. But then you look further, and now you consider just the subpopulation of men. And again, you do the same thing. You ask what fraction recovered among those who took the drug, what fraction recovered among those who didn't take the drug, and you find that the inequality goes the other way. So for the men, there was a higher rate of recovery among those who didn't take the drug. And the surprising thing is that if you look at the women, it also goes the other way. So again, higher rate of recovery among those who didn't take the drug. So this feels like a paradox because you might naively think, well, if you're a man or a woman, you should not take the drug. But if you're a member of the general population, you should take the drug. And that's a paradox. If you haven't seen this before, let me just persuade you that it can really happen with some actual data. So imagine we had the following experiment. So imagine 300 men took the drug and 180 recovered. That's a 60% recovery rate. 100 didn't take the drug, 70 recovered. That's a 70% recovery rate. So among the men, the rate of recovery is higher for those who didn't take the drug. Here are the women. 100 took the drug, 20 recovered. 300 didn't, 90 recovered. That's a 20 versus 30% recovery rate. So again, higher among those who didn't take the drug. But then when I take the totals, so there's 400, I just summed the denominators, 400 people took the drug and summing the numerators, 200 recovered. That's a 50% recovery rate, whereas over here, 400 took the drug and only 160 recovered, which is only a 40% recovery rate. So on the totals, it goes the other way, and the rate of recovery is better among those who took the drug. So the question is, how do we resolve this paradox? And I think the important thing to bear in mind here is even if you have a kind of formal resolution, maybe you can show that there's no logical inconsistency in how we use probability theory. At the end of the day, what you're going to want to know is, should you take the drug or not? So whatever solution gets proposed, it should answer the question of, if this is the data you have, what should you do? It should inform your actions. Okay, so the resolution involves going deeper than the statistics and looking at the causal structure. So why does it look like a paradox? Well, here's an explanation of why it seems paradoxical. I think we all, in the back of our heads, have this kind of causal structure in mind. So we think, for example, that the treatment might influence recovery, and maybe also the gender. So maybe men and women recover from this condition at different rates. And if this is what you think is going on, then it's actually impossible to get this kind of situation. Because if this is what's going on, then to compute the stuff on the top line, for example, the probability of recovery given that you took the drug, all you have to do is take a weighted sum of these two probabilities, weighted by the probability of being a man and the probability of being a woman in this population, and you'll get that. So if I just take the weighted sum of these two equations, obviously I'm not going to get this equation, I'm going to get the opposite inequality. And that's the appropriate thing to do if this is the causal structure. The resolution of the paradox is that this is not the causal structure, this is the causal structure. So in this experiment, it was not a randomized trial, but the gender of the members of the population had an influence on whether they decided to take the treatment or not. So if you look back at those statistics I showed you, you'll notice that the men were much more likely to take the drug than not, whereas for the women they were much more likely to not take the drug than to take it. And so the idea is that in this kind of experiment, you can imagine that the men, for example, both have a higher rate of recovery naturally, regardless of whether or not they take the drug, and they're more inclined to take the drug. And therefore, if I then ask you, suppose I have a member of the population, and all I'm going to tell you about them is that they took the drug. What do you think about whether they recovered or not? Then you can reason as follows. Well, if they took the drug, they were more likely to have been a man, and if they were a man, they're more likely to have recovered. And therefore, the evidence that you've given me of them having taken the drug gives me a reason to believe that they were more likely to have been a man, even though the causal influence of drug on recovery goes the other way. The drug is not useful for recovery. So the point is that these conditional probabilities up here were really, that these correlations are really sometimes just about common causes. Treatment can inform me about recovery because they're connected by a common cause, not because the treatment is influencing recovery. I can get correlations from a cause-effect or a common cause structure. And so in this experiment, ultimately these are the ones we should trust, that you should not take the drug. And this correlation between recovery and drug, it's just due to the common cause that's set up by the gender influencing the treatment and the recovery variables. So the moral of the story is that you can't just look at the data table and say, here's how I'm going to act. You have to do a deeper analysis of what does this data table tell me about what the causal structure, possible causal structures of this experiment are if you're going to want to build your actions. So my argument is that the same thing is true here, that if we're an instrumentalist and we say we just have the data table, I want to say that's not adequate, because what we want in an explanation of the statistical correlations we see is a causal account of how they arose. So in particular, we'd like to know, for instance, this correlation that we see between x and y for different values of s and t. Does it necessitate, so if I give my particles names, a and b, does it necessitate that the setting variable s influences b directly? Or could I get away with, for example, a common cause acting on a and b to set up those correlations? This is exactly the sort of account that I think would really constitute an explanation of this experiment. And I would say that if we want our understanding of quantum theory to parallel what we consider to be a proper scientific explanation elsewhere in science, then it really has to provide causal accounts. I think elsewhere in science, where we're not satisfied with correlations, like in a drug trial, no one would be satisfied with mere correlations. You need to have a causal account. I would also say that if we want to know how to extend quantum theory to places where perhaps we haven't applied it yet, like to Einstein's theory of general relativity, then we really need to answer this question, because Einstein's theory really takes the causal structure. It's one of the most significant things in theory, and it's dynamical. And if we can't make sense of what's going on causally, even for a simple experiment like this one, if we can't decide whether it's this or this, then I don't think we have much hope of extending quantum theory to cover general relativity. Okay, so for all those reasons, I'm committed to a principle that says statistical dependencies have to be explained causally. So that's going to be my first supposition. And in fact, that's the only notion of realism that I'm going to be committed to in this talk. And I think it's a good one. You can take different views about what counts as a causal explanation, but this principle is basically saying there has to be a causal explanation, however you want to make sense of that. Okay, on to the second principle. So this is one that I think is extremely productive in physics and important, but we hardly ever hear about it, and it's Leibniz's principle of the identity of indiscernibles. So let me give you a couple of quotes. So this is Leibniz. To suppose two things indiscernible is to suppose the same thing under two names. And the place where he used this principle in a physics context was his discussion with Newton, his objection to the notion of absolute space. And I won't read this quote, but the idea is something Leibniz says as a criticism of Newton's notion of absolute space. If I imagined taking every particle in the universe and moving them all over by some fixed amount relative to absolute space, but not changing any of the relations between them, nothing that we observe in the universe, in principle, would change. Leibniz wants to say, I'm not imagining a different universe. If nothing that we could possibly observe would change, we should consider these two universes I've just described as being exactly the same. And therefore, the relationship of these particles to absolute space is not a real physical degree of freedom, and only the distances between the particles are real physical degrees of freedom. That's the idea. So, to generalize it, the point is that it presumes that when you have things that are empirically indiscernible, then your physical theory should say that they're ontologically identical. So the reality that you posit is constrained by what can be observed in principle. And it suggests a kind of methodological principle for how you should build physical models, which is that if you, let's say you have a physical model, and you notice that there's two scenarios that your model predicts are empirically indistinguishable in principle, meaning the model says no matter what you do, you'll never distinguish these two scenarios, and yet your model represents them as ontologically, i.e. physically distinct, then you should reject the model and replace it with one that makes these two scenarios ontologically the same. That's the idea. Okay, so I said that this principle has been useful in physics, even though as physicists we never hear about it. And I think that's strange, because ultimately I think I'm going to try to make the case that this has been one of the most successful methodological principles that we've seen in physics. So what are its credentials? And it's mostly this guy, so I'll give you a few examples. So Einstein likely read Leibniz, but also Mach was a big fan of Leibniz's work, and Einstein was certainly influenced by Mach, so presumably Einstein's endorsement of this principle does go back to Leibniz. And so where did he use it? Well, in the 1905 paper that introduced special relativity, on the very first page, he describes an objection to the ether theory. Right? So he's building an argument against the existence of an ether. And he uses this induction experiment. He says, consider the following two scenarios that are ontologically distinct according to the ether theory. One, there's a metal loop which is at rest with respect to the ether, and there's a magnet that's moving with respect to the ether through the loop. The other, where it's the magnet that's stationary and the loop that's moving over it. So Einstein says, well, in this situation, what you have is a time-varying magnetic field, which creates an electric field, which creates a force on the electrons, induces a current. Over here, you have a static magnetic field, but electrons in the loop are moving through space, and so they feel a Lorentz force, and it also induces a current. And Einstein notes that the currents that are induced are precisely the same, and he says there's nothing in the phenomenology of what you observe here that can distinguish these two scenarios. All that's relevant for the current that's induced is the relative motion of the magnet and the loop. And their absolute velocity relative to the ether is irrelevant to all empirical phenomena. So Einstein says we must therefore reject any theory that makes that distinction between these two scenarios, given that they don't lead to any observable differences. So that's his first use of it. His second use of it is in the strong equivalence principle. So a similar sort of argument. He says, imagine doing any experiment you like inside an elevator which is at rest in a gravitational field. Do all the same experiments in an elevator that's accelerating uniformly through free space. Nothing you observe in principle can tell the difference between those two scenarios, assuming this gravitational field is really uniform across the space of the elevator. So Einstein concludes, we should try to build a theory where the explanation of those phenomena is exactly the same in these two cases, and that's what general relativity achieves. It's, the curvature of space-time is inside this region is exactly the same in these two cases, and so the explanation of the similarities of what's observed is exactly the same. And then one final example, in the last step towards building the general theory of relativity, Einstein needed to overcome a confusion about the nature of diffeomorphisms and generate his principle of general covariance. And it basically came from what the philosophers call the whole argument. Einstein imagined some fixed region of space-time where you apply diffeomorphism only inside that region. And he noted that outside that region, everything you observe would be the same, regardless of which diffeomorphism you applied inside. And therefore, he concluded the diffeomorphisms are not physical changes, and therefore, the physics has to be invariant under these diffeomorphisms. The diffeomorphisms are not part of the ontology of the theory. Okay, so for all these reasons, I think Leibniz's principle really stands at the base of a lot of modern physics. And I'm going to show you what it implies for our interpretation of quantum theory in a little while. But I think it's worth. I think many people share this intuition that it's a good principle. And what's nice about it is that it makes a bridge between things that you observe and the kinds of ontology you postulate in your physical theory. All right, those are the two principles. So now I want to talk about how we're mathematically going to model causal structure so that we can ask whether we can have a kind of causal account of quantum correlations. So I'm going to follow the approach that you could read about in Pearl's book on causality. So this is the approach that's used by statisticians and people in the field of machine learning to model causation. I'm going to tell you very little about this formalism, just enough for us to use it. Importantly, in this approach that I'm taking, the causal relationships between systems are going to be taken to be ontological. They're facts about the world. Whereas the probabilities that we assign to the values of variables, for example, are taken to be the degrees of beliefs of agents. So these are epistemic probabilities, and they just quantify agents' beliefs. Okay, so what is a causal model? It's got two parts. The first I'll call the causal structure. So it's formalized by a directed acyclic graph. So you could use any directed acyclic graph. The nodes are random variables, and the edges represent direct causal influences. So I've used a particular graph that's going to be useful in this talk, but really I could draw any DAG here. And supplementing the structure are parameters, which I will just call the causal statistical parameters, and the rule is that for every variable, for example, x here, you need to specify the conditional probability that the variable takes any of its values given its parents. So for every possible set of values of its parents, what's the probability distribution I assign over x? So here's for y. And then for the cases where they have no parents, you just specify the marginal distribution of that variable. And then it's not hard to show that the overall distribution you should predict for the set of all these variables is just the product of these distributions. Okay, now in particular, if there's some variable you don't observe, like say this lambda down here, then you sum over the values of that variable and you get a distribution over the rest of them. So that's how a causal model predicts statistics for some set of variables. The problem of causal inference is to solve the inverse problem, that you've taken some statistical data, you write it down as an estimate of some joint distribution, and then you ask yourself which sorts of causal models could have given rise to that experimental data. So that's what we're going to be interested in. But first, let me point out to you how this formalism has already embodied the first of our principles. Right? So this Reichenbachian principle that any statistical dependencies need to be explained causally is really baked into this whole formalism. So, for example, we presumed that the joint distribution over S and T, for example, doesn't involve any correlations, that P of S and, I don't have a PST here that allows correlations. And that's because any correlations I want to encode have to be due to a causal connection. So either there has to be an arrow from S to T or maybe a common cause of S and T. And if I'm saying that those arrows are not there, then I have to say that they're statistically independent. Okay? So this whole formalism really starts from Reichenbach's notion. But there's one other principle that gets used in these causal inference algorithms, so I need to explain that principle to you. So let me give you a simple example of a causal inference problem. So if I have three variables, A, B, C, so there's some joint distribution over all of them, and it turns out that A is statistically independent of B. So that means if I take the marginal on AB, I find that it factorizes. So suppose that's the case, and furthermore, there are no other independences in this joint distribution. So A is correlated with C, B is correlated with C, and also there are no conditional independences. Like if I look at B and C conditioned on A, I find that they're correlated, and A and B are correlated if I condition on C. They're only uncorrelated if I haven't conditioned on C. So suppose that's the situation, and then you ask, what is the causal structure? So let me put it, some of you have probably seen this before. For those of you who haven't seen this before, can you guess what the causal structure must be? A pointing to C and B pointing to C, like that. Yeah? Yes, that works. Let me just mention that if you try to do it the other way, for example, C points to A and C points to B, then generically you get correlations between A and B, like the case of gender with the treatment and recovery variables. Those would be correlated, and here we have them uncorrelated. And this causal structure makes A and C correlated, B and C correlated. Sorry, this causal structure makes A and C correlated, B and C correlated. And it also has this lack of conditional independence, that A and B become correlated if I condition on C, because C is a common effect of A and B. So yeah, that does it. That works. And that's a possible causal explanation of what this pattern of correlations we've seen. And now the reason I need another principle is because there are other logically possible explanations, like this one. So here, C is a common cause of A and B, and there's a direct influence from B to A. And the point is that I can choose these parameters very carefully so that the correlations between A and B go away. So it could be, for example, that A and B are positively correlated by virtue of the direct cause and maybe negatively correlated by virtue of the common cause, and those two effects precisely cancel to make them uncorrelated. And so the difference is that here, that cancellation is only going to occur for very particular values of the parameters in the model, whereas over in this model, I will find this independence for all choices of these parameters. Yes?
Does this mean that we can ignore how we have found out that A and B are independent? So we have found it, and this is being already, and we can ignore this process, and we can concentrate only on the next step.
Yes. So certainly here, to make the example simple, I've assumed that A, B, and C are the only causally relevant variables. So I've assumed that we're looking to find a causal structure among A, B, and C alone. In general, we might ask, well, might there be some other unobserved variables that could be common causes of these guys, and that could also explain what I've seen? So there'd be a larger set of models. But that's right. You don't, for this kind of analysis, you don't need to know why they're, or how they were formed. The principle is to say, well, even though this is a logical possibility, it's a much worse hypothesis than this one, because it requires your explanation to be fine-tuned. This explanation only works for a set of measure 0 of the choices of these parameters, whereas this explanation works regardless of the values of those parameters. So this is one of the principles that people in the communities who use these causal inference tools always endorse to try to narrow down on the set of causal possibilities. All right, so I'm going to assume it here for the time being and ask what it implies about the causal structure of quantum experiments. And then later I'm going to talk a little bit about how it relates to Leibniz's principle. Okay, so let's go back to our quantum experiment. So remember, this is the kind of data we saw. And now the question is, what sorts of causal relations might exist between our two setting variables and our two outcome variables? That's the kind of problem that these causal inference techniques were designed to solve. So a very natural assumption for what's going on is this one, that there's some unobserved variable that corresponds to the properties of this pair of particles early on, which is influencing both x and y. It's a common cause, right? So these particles were together in the past. So there's some common cause that acts on x and y, and that's why we see correlations between them. It seems like a very natural assumption given the structure of this experiment. Turns out that that explanation doesn't work for this data. So that's due to John Bell. That result is due to John Bell. This is a way of interpreting Bell's theorem, basically saying there's certain causal explanations of correlations that just don't work. So to explain why that is, let me change the data table slightly. So here you notice that there's a bunch of probabilities that are almost 0.5. Let me just make them exactly 0.5. These are called the Popescu-Rorlich box correlations. It just makes the discussion a little bit easier. So why can't I generate these correlations in this causal structure? So first of all, let's look at an individual row. So this row here has x and y perfectly correlated. So that's very easy to generate here. I could, for example, make lambda just a coin flip, a fair coin flip, and then make x and y copies of lambda, and that would generate this sort of pattern. This bottom row here has x and y anti-correlated. When x is 0, y is 1. When x is 1, y is 0. So I could also do that by making lambda coin flip, and then x is a copy and y is an anti-copy of the coin, and I generate anti-correlations between x and y. The problem is that if I want to, for example, consider the case where s over here has value 1, so I'm in one of the bottom two rows. So now I have to generate correlation or anti-correlation depending on the value of t. And so now the question is, how does x know whether to be a copy or an anti-copy of lambda? Right? It has to toggle between the two depending on the value of t. But there's no causal pathway from t to x, so it has no way of knowing, so there's no way to get these correlations. More generally, you can show that this assumption of this causal structure, together with any parameters of this form, gives you a probability for x and y given s and t of this form, and you can show that these sorts of probabilities satisfy certain inequalities called the Bell inequalities, and these statistics I showed you here violate those Bell inequalities, and so even these statistics are inconsistent with this causal structure, even though they're not perfect like the ones we saw before. Okay, so we can definitely rule out this causal structure as a possible explanation of of these statistics. So then we go looking for other causal structures. So you say, well, what about this one here, where the setting on the left has an influence on the outcome on the right? That's the kind of thing you'd expect to need to generate this. Like, whether y is a copy or an anti-copy of lambda can now depend on the distance setting, and we should be able to generate the correlations we're interested in. So this is a logically possible explanation, but it turns out it's fine-tuned. And the reason is that in this setup, the statistics of y are independent of s. So, for example, if I imagine looking at the probability that y is 0, that's the sum of these two columns, the probability versus the probability that y is 1, it's really independent of the value of x. There are no signals that I can send by toggling s. I can't change the statistics of y. So s and y are statistically independent. And if there was a causal arrow from s to y, I would generically, for generic values of the parameters, I would expect them to be dependent. And so the only way this can explain the independence of s and y is if I fine-tune the parameters in that model and make sure that the kinds of correlations that could be induced here are washed out maybe by some noise being added to y. But if we adopt the principle that you shouldn't have fine-tuned models, we have to exclude this and say it's not a good explanation of what we've seen. And the same goes for other attempts to try to explain Bell inequality violations. Maybe I should say that usually many people reject this kind of explanation on the grounds that I can do this experiment where the measurements of the two wings are so far apart that light doesn't have time to communicate the setting of the left before the outcome on the right has to be reported. So we can appeal to the space-like separation of these events in relativity to say that there should be no causal influences. So you might think that the content of special relativity is that not just signals, but any causal influences should not propagate faster than the speed of light. So that might be one reason for dismissing this. And what I'm saying here is that one way to articulate the tension between allowing for superluminal causation, even though there are no superluminal signals, is that to achieve that, you have to fine-tune. The only way you can have superluminal causes without superluminal signals is if the parameters in your model are fine-tuned. And so it's just a way of formalizing what the tension between positing those two things is. All right, here's another attempt at explaining, providing a causal explanation of Bell correlations. It's the idea that the setting variable on the left actually isn't freely chosen. It's actually influenced by some common cause, which also influences something on this wing, such as the outcome. So people often dispute this sort of model on the grounds that we have free will, there aren't systems that constrain my choice here and influence things far away. But regardless of what you think about the status of free will, you can also recognize that this is a bad explanation if you endorse no fine-tuning, because generically, if I have a common cause of two variables, they tend to be correlated. And the only way I can make sure that there's no statistical dependence between s and y is if I fine-tune the parameters in this model. So we can rule that one out as well. You can also talk about causes that go backward in time, say s to lambda to y. Same thing, generically we'll set up correlations. So this kind of model would have to be fine-tuned. And so you can ask, well, what about any possibility? For all the possible directed acyclic graphs I might draw, are there any of them that can explain these correlations? And the answer is no. Either they just can't do it because they satisfy Bell inequality, right? It's a causal structure that satisfies the Bell inequality, or they can do it, but it's fine-tuned. Okay, so this is a theorem that's proven in here. All the causal structures have those features. So this is a way of seeing just sort of a new way of casting Bell's theorem. And so what are the assumptions we've put in? We've assumed that these statistical dependencies should be explained causally. We've assumed this principle of no fine-tuning. We found a contradiction with this statistics, which means that we have a contradiction with quantum theory and with the experiments that corroborate quantum theory. Okay, so this is a different way of describing Bell's theorem than the usual way. So this would be the usual kind of scheme. You'd have something like an assumption of realism, an assumption of locality, meaning that there aren't any superluminal causal influences, an assumption of free will or no superdeterminism it's sometimes called. There's the common causes of the settings on one side, the outcomes on the other. An assumption that you don't have causes that propagate backward in time. So this is, in a sense, how we usually would think about Bell's theorem. And this alternative approach is different because, first of all, it's a bit more specific about what this realism is doing. It's saying, in this approach, that the only notion of realism we need is that there should be a causal explanation of what's going on. And then this no fine-tuning assumption basically allows you to derive all of these assumptions from the empirical fact that we see no signaling. We don't see any correlation between the setting on one side and the outcome on the other. That, together with the no fine-tuning principle, allows you to derive that there should be no superluminal causal influences from S to Y, and no superdeterminism and no retrocausation. That's what we went through in the last few slides. So this no fine-tuning principle acts as a nice kind of umbrella for all these different assumptions that we would usually have. Okay. Now, I would say that this is pretty fundamental, but there are perhaps unobjectional ways that you might have fine-tuning in your models. So, for example, if I have like an equilibration process and the one distribution I need to make my explanation work happens to be the thermal distribution, then you might say, well, okay, the thermal distribution is a set of measure 0 relative to all distributions, but it's also the endpoint of an equilibration process. So maybe there are circumstances in which fine-tuning has a kind of dynamical explanation. So I think that's right, that this isn't as great a principle as you might hope for. So it would be much nicer if we could replace it with Leibniz's principle that I told you about earlier. So I want to show you that you can, in fact, do that you can generalize this no fine-tuning principle. So remember our drug trial, where we had this joint distribution over these variables, and we had ambiguity about the conditional probability of recovery given treatment, because of the two ways they were connected. Well, one way you can do a drug trial so that there is no ambiguity is by doing a randomized drug trial. So what you do is you come in and rather than just measuring, asking somebody whether they took the drug or not, you might ask them that, but then you flip a coin and you administer either a placebo or the drug. And so now you've disconnected, there's no causal connection between what the patient preferred treatment was and what the assigned treatment was. So you've come in, you've intervened, and you've made their treatment independent of any influences in the past. So now if you see a correlation between recovery and the assigned treatment, you can conclude that it wasn't due to a common cause, and so it's really representative of a cause-effect relation. So what that means is that there's a difference between the conditional probability of recovery given that you have observed that somebody took the drug, and the conditional probability of recovery given that you made somebody take the drug, irrespective of the causal influences that would naturally determine their behavior. So in this causal inference literature, they actually have a distinction between these two kinds of conditionals. This is sort of a critical distinction. They're not the same. And so the fine-tuning principle is really about situations where you don't have any of this interventional data. You just have the observational data. And it says, look, if you've seen statistical independence, like P of A and B is independent of B, and yet you posit that B causes A, well, that's a fine-tuned kind of explanation, like the example we saw. But you might also have a circumstance where you have actually this interventional data, and you find that even if I intervene on B, I still don't change the statistics on A, regardless of how I intervene on B. If somebody nonetheless has a model that says B causes A, despite this independence, that's also a kind of fine-tuning. It's a fine-tuning for these interventional models. So that seems really surprising. How could it possibly be that this is true, and yet B still causes A? So let me give you an example. It's the Vernam cipher from cryptography, also known as the one-time pad. So the idea is you have 3 strings. One's called the plain text, which is the message you want to send. You have a key, which is a bit string, each bit of which is chosen uniformly at random. And you have a ciphertext, which is just the sum mod 2 of every bit from your message and the corresponding bit in the key. So causally what's going on is that the plain text and the key both influence the ciphertext. The ciphertext is just the sum mod 2 of those 2 strings. Take the simple case where these are just single bits, right? So it's just the sum, and the critical thing is that this key bit has to be uniformly distributed over its 2 possible values. That's the only way it works, right? That means that when I see a particular cipher bit, it's like if I got 0 here, and I ask what are the relative probabilities of the plain text bit being 0 or 1, the answer is it's equally likely that it was one or the other, because the key was equally likely to be 0 or 1. So I get no information about the plain text from reading out the ciphertext. That's called information theoretic security. So in this context, if I ask what's the distribution over C when I intervene on the plain text and I make it take a particular value, well, the answer still is going to be a uniform mixture of C being 0 or 1, because C still depends on that key. And that's exactly what the marginal distribution on C is. And so even though I intervene on the text and change its value, the distribution over C remains the uniform distribution. So I have this feature that there doesn't seem to be any influence of my intervention, and yet clearly, given that I've explained how the whole thing works, it's clear that the plain text has an influence on C. That's clear, because I can always get the plain text out of C if I bring in, the key back and I add it to the ciphertext. So this is an example of fine-tuning of the sort we saw on the previous slide here, this kind of fine-tuning. But now notice that in principle you could go and find that key, and if you had knowledge of that key, then intervening on the plain text would surely influence the distribution of the ciphertext, right? Like for different choices of text, the ciphertext would change. So if you've got access to the key, then you can see that the plain text really is a cause of the ciphertext. Okay? So you could go looking for it to vindicate this model. But suppose that your physical theory says that even in principle, there is no variable that you can find in the world that will make your interventions on B change the distribution on A at all. And yet your physical model still says that B causes A. Well, that's a violation of Leibniz's principle. Because, if I imagined a world where there were these sort of one-time paths happening, but nobody could ever access the key, then, a different world where I flipped the value of the key would be empirically completely indistinguishable from the first world. There would be nothing you could do to distinguish which world you were living in. And therefore, Leibniz's principle says you should not posit that there are different worlds in that case. So yeah, anytime you sort of have something that's in principle, you're unable to see the consequences of this causal influence in any experiments you do, that's going to be a failure of Leibniz. So let's start with that idea instead. So here in our experiment, it is true that if I intervene on the setting x, I don't just observe it, but I make it take a particular value, and I ask, what's the consequence for y? I don't see any change in the distribution over y. And I go looking for other variables that might help me see the influence that S has on Y, and I find none. And in fact, relativity theory says necessarily you will find none, because if you did, you would have a superluminal signal. You'd have a channel from S to Y that would allow you to send signals faster than the speed of light. So if I believe relativity theory, it says in principle there is no way that you can send those signals, and therefore you have exactly a failure of Leibniz's principle if you posit that there's a causal influence here. Because it's a causal influence that will never be corroborated by an intervention on S. So you can indeed rule out these kinds of models based on Leibniz's principle. So here I've just summarized it. If you think that this is true because of relativity, then you have to conclude that S is not the cause of Y in those models. Okay, now one small comment here. The contrapositive of this inference is that if you assume that S is a cause of Y, then it implies that intervening on S should allow you to change the distribution over Y if you have some background knowledge. And therefore, you should be able to signal superluminally. And this actually is a very nice account of the point of view that Anthony Valentini takes on quantum theory. So I know you had a lecture by Anthony in this series. So he, like all Bohmians, endorses the notion that there are these non-local actions, causal influences in quantum theory. But unlike most Bohmians, he is committed to something like a Leibnizian principle. And so he concludes that given that causal action is there is some stuff out there that would allow you to use, you could find out about and achieve superluminal signaling. So from Valentini's point of view, there are some hidden variables that you come to learn about such that you would now be able to sends signals faster than the speed of light, and it's just a contingent fact about the epoch of the universe that we live in that it's hard to get that information, but in principle we can get it, and when we do that, we're going to find that relativity theory is wrong. So that's one way, that's an avenue you can take. It respects Leibniz's principle, it achieves a causal explanation, but it has the high cost of saying that relativity theory is wrong, quantum theory is wrong, and there's some other theory that's going to replace it. So personally, I don't think that's the case. I think that relativity theory is going to continue to be shown to hold experimentally, and I think quantum theory, as far as it goes, is right. So I'm not inclined to follow Valentini's path on this. I would rather say that there just is no causal influence from S to Y in these sorts of experiments. So the bottom line is that I can replace this no fine-tuning assumption in my argument with Leibniz's principle. So now I have these two principles that I started the lecture with, and they imply a contradiction with quantum theory and an experiment. And so this is what I meant by what is the challenge to scientific realism that quantum theory poses. So for me, because I think these two principles are very good principles, and this argument shows a contradiction with quantum theory, this I think is the best way of formulating that challenge.
Would one need to include that special relativity is correct as a third?
Well, when I said here contradiction with quantum theory and experiments, I'm presuming the correctness of quantum theory, in particular relativistic quantum theory. So you could say, well, maybe quantum theory is wrong, and so it's still a contradiction with quantum theory, but perhaps maybe not experiment, that future experiments would find that they don't accord with quantum theory. So yeah, Valentini is banking, for example, on that being the way out, that you could have these kinds of things, but in fact it's relatively something different. But I'm imagining that this is going to continue to hold up in the future. Okay, good. So what do you do when your principles lead you to a contradiction, and you're not willing to give up on any of those principles, which is my situation? You go looking for other implicit assumptions in the argument. So the implicit assumption in the argument that I've given you thus far is that the way I formalized the notion of causal model, I had these graphs with nodes. Some of those nodes were unobserved, and I presumed that they were described by variables that could take one of a set of possible values, and that inferences you make, like the way you formalize your incomplete knowledge, was with classical probability theories or probability distributions over the values of variables. So that was baked into the framework that we were using to derive all these contradictions. And my view is that this is the assumption that has to go, that we should stick to these principles and entertain the possibility that the way we describe our incomplete knowledge of reality is not classical probability theory. That in a quantum world you need to you can be conservative about the causal structure, but you need to be radical about how you formalize epistemology, how you make sense, how you accurately describe your incomplete knowledge. So that's the idea. And so instead of having this framework of classical causal models, I think we need a framework of quantum causal models, by which I mean, first of all, that the unobserved variables get replaced by unobserved systems. So these systems now are not going to be something like a hidden variable that just takes one of a set of values, but something more exotic. And furthermore, that these conditional probabilities that were the parameters in the classical models are replaced by a new sort of mathematical object that describes an agent's beliefs. So I'm not going to bother to define this carefully, but rho C here is just a regular density operator on the system C, and these notations refer to operators on a Hilbert space of C, X, and S. So even though X and S are classical variables, I can assign them a Hilbert space and some special basis of that Hilbert space, such that they're diagonal relative to that basis. So this is just a way of writing an operator on these three systems, and it's going to play the same role as this conditional probability. It's going to encode what an agent believes about X for any beliefs that they might have about S and C. So how to propagate their beliefs about S and C to X. There's going to be some complex value matrix that does that rather than a probability distribution. So the shape of the causal structure imposes some extra constraints. So these guys here have to commute on C, the Hilbert space they share in common. And you have formulas for computing things like the joint probability of x and y given s and t, which looks like this. And if you do things this way, you can actually violate the Bell inequalities and explain the quantum statistics. But you really need to be committed to the idea that these objects, which are essentially encoding things that we normally see in the quantum formalism, have to be interpreted in the same way that these objects are interpreted classically, namely as the degrees of belief of some rational agent. So that's, I kind of want to persuade you that we really need to do that. We need to think of quantum states as being the analog of probability assignments for this kind of program to work. Okay, so that's the next part. I just want to argue that for this to work, I really need quantum states, all quantum states, in particular pure quantum states, to be epistemic. So what do I mean by this difference, ontic versus epistemic? So roughly speaking, if I have two non-orthogonal quantum states, psi1 and psi2, then to take an ontic view of those quantum states is to say that those two things are describing different ways the world could be. So when I think of these two quantum states, I'm thinking of different worlds. Whereas over here, it would just be two different ways of having incomplete information about the world. But the world could be in some fixed state consistent with both those quantum states. That varying the quantum state need not correspond to a variation in any properties of the world according to this point of view. So it's useful to have some cartoons for this idea. So if I imagine my space of physical or ontic states to be labeled by lambda, this kind of point of view is one where you might say, oh, psi1 and psi2, those are different points in that space. Whereas over here, psi1 and psi2 are a different pair, different distributions over that space, but distributions that might overlap. So these two distributions overlap in this corner, which means that the physical states in this corner are consistent with both of those distributions, so they're consistent with both of those quantum states. That's the idea behind this difference. Okay, so let's go back to our simple, our Bell-like experiment, and let me cast it in a slightly different form so that you can be persuaded that this epistemic interpretation is really critical if I want to have a common cause explanation of what's going on here. So you'll remember in quantum theory that if I want to make predictions about these correlations, one way I could do it is by registering the outcome, the setting and the outcome here, and updating the quantum state of system B as a result of what I've measured over here. So if in this experiment I set up an entangled state between A and B, and the reduced density matrix on B is the completely mixed state, that's this guy here, then when I register S and X, I update to some pure quantum state for B. So for example, I might be doing one of two measurements over here, and if I'm doing the first measurement, S equal to 0, then maybe I collapse B to being this or this quantum state, psi naught naught or psi naught 1. And the second measurement, where S is 1, for each of the two outcomes I get on it, I collapse the quantum state of B to a different pair of states, a different pair of orthogonal states. So this is part of what the formalism of quantum mechanics predicts, that you should update the state you assign to the distant system based on the outcome of the experiment you did here, in a way that depends on what measurement you did here. Okay, so what does an ontic point of view on the quantum state say for this remote collapse? So in an ontic point of view, these four different vectors all correspond to different physical states. And so what's happening in this experiment is that if I choose one setting here, then depending on the outcome I get, I'm going to either prepare this red state or that red state, whereas if I have the other setting, I prepare this blue state or that blue state. And so what you see is that although it doesn't fix what the reality on the other side is, it fixes the menu of possibilities. So my choice of S fixes the menu of possibilities to be either the red possibility or the blue possibilities, and those two sets are distinct. So my choice of setting over here has influenced the possibilities for the reality on B. And the only way to explain that is if there's a causal influence from S to B. So it's like the treatment influencing recovery in the drug trial. It has to be modeled by this kind of diagram, where my choice of the setting here influences the physical state of B. So this is going to be a non-Leibnizian explanation because that choice of setting over here will never allow me to change the distribution over y if quantum theory and relativity are correct. And so the change in the physical state on B never gets manifested at the empirical level. No matter what measurements you do on B, you will never see the difference in the real possibilities for B that was induced by that change in S. So this is a non-Leibnizian model of what's going on that requires these superluminal causal influences. On the other hand, if I take psi to be epistemic, then this basis, for example, this orthogonal basis of states could be one way of partitioning up the uniform distribution on the space into two distributions, one in the upper, one in the lower hemisphere. This blue set of states could be a different way of partitioning that uniform distribution into the left or the right regions. And so now what happens in these experiments is that when I choose the setting S equal to 0 here, then depending on the outcome, I just update my knowledge of the physical state of B in one of two different ways. So I might learn that it's in the top half of its state space or in the bottom half of its state space, depending on the value of x hat mod. Whereas when S is 1, all I'm doing again is updating my knowledge, but I'm just updating it differently. Right? So what we can imagine here is that A and B might be, for example, perfectly correlated in their properties. And these two measurements on the left-hand side are just asking, is it in the upper or the lower? That's for S equals 0, and for S equals 1, is it in the left or the right? And so when I learn that the state of system A is on the left, I can immediately infer that the state of B was on the left as well, because their properties were correlated by virtue of the common cause. So in this experiment, I can imagine that system B has some fixed physical state all along, which is not changed by my choice of setting here. And all that changes as a result of my choice of setting is how I update my knowledge of where that physical state lies in space. I have the option of updating it so that it's now, known to be in either the top or the bottom, or known to be on the left or the right. So if it was in the top left corner, for example, after the measurement's done, I know that it's somewhere in the top. After this measurement's done, I know it's somewhere on the left. And because of the complementarity of measurements in quantum theory, I can't find out both pieces of information, so I have to face this trade-off. What do I want to learn about the distant system? I can update my knowledge in two ways, but I can't influence it. So this is like the treatment informing us about recovery, right? So the idea here is that learning the values of x and s merely inform us of the properties of B. They don't alter or influence the properties of B at all. And it has this causal structure, just the common cause, the one that's consistent with relativity. And it's a Leibnizian explanation of what's going on here because it explains the fact that no measurement you do here will have its statistics depend on S at all because there's no causal influence between them. So there's no problem explaining that lack of dependence of the statistics here on S. I should expect that from this causal structure. So that's the cartoon version of why it is that if you want to achieve one of these Leibnizian common cause explanations of these types of experiments, you have to grant that the quantum state that you're collapsing the distant system to is just a description of your incomplete knowledge in this sort of way. It turns out that in my view, all the good no-go theorems we have about how to interpret quantum theory can be recast in the way I've recast Bell's theorem for you, as essentially being a contradiction between quantum theory and these two principles, Reichenbach and Leibniz. So I'm not going to say much about this, just give you sort of a general sketch for the diversity of phenomena that look like this. So suppose I have an experiment that is just like, a preparation followed later by a measurement, and I just get some statistical data that correlates the measurement outcome to the setting of the preparation. Having a classical causal model means I should just think of this system A as having some set of ontic states, physical possibilities, and there's a variable ranging over those guys. And this preparation is just preparing a distribution over that variable for every value of S. And this measurement is just revealing something about the physical state of the system that passes between them. So it's just a conditional probability of the outcome Z given the ontic state of the system. And I compute the statistics by just summing over the unobserved variable, this lambda that acts as the causal mediator between them. So that's what a causal model is. Now, if I have a more general sort of thing where everything has a setting and an outcome and maybe there's some transformations that appear between the preparation and the measurement, So now the data looks like this, correlation between all the outcomes given all the settings. I can, again, just write down a classical causal model for that, where every one of these guys is just a conditional probability of the outputs given the inputs. And I can write down a formula for the statistic. So this is all just causal models for general experiments. And even though I've drawn things this way, I mean, one of these boxes, this wire here could be a composite system. It could be lots of systems, and these boxes could act trivially on some of the systems. So the first, here's a couple of examples. It could be that this is the structure of the experiment, or this is the structure where the final measurement is on two separate systems. This looks just like our Bell experiment, drawn differently. So that's the first way in which this Leibnizian principle comes in, that if I want my classical causal model to satisfy Leibniz's principle, it's going to have to respect this causal structure, just like we saw for the Bell case. Even in any kind of causal structure you draw, you're going to have the conditional probabilities respecting how things are wired together. Okay, so that's a non-trivial constraint, and it doesn't hold just for Bell. You can really write down any experiment you like, look at the causal structure. For your model to be Leibnizian, it's going to have to respect that. So you can derive new no-go theorems that go beyond just the causal structure of the Bell experiment and appeal to other causal structures. A second thing you can do using Leibniz's principle is get a constraint on the kinds of conditional probabilities you can assign to given experimental procedures. So if I have a setting variable here that really determines exactly how this preparation procedure works, it could be that for two very different preparation procedures, nonetheless get represented quantum mechanically by the same density operator. Right? So lots of ways that could happen. I could use a piece of Polaroid or a birefringent crystal. It won't make a difference to the quantum state that represents the polarization of light. Or I could mix together Z spin eigenstates or X spin eigenstates. Those are both equally good ways of preparing the completely mixed state of a spin. And so the idea is that any measurement I do following a pair of such preparations will give exactly the same statistics. Right? When the density operators are the same, that means that all experiments down the road have exactly the same statistics. And so it should be that the conditional probabilities I use in my model to represent those two things are the same. Otherwise, I would be positing different distributions over properties, even though those differences never get manifested down the road in any experimental statistics. That would be a violation of Leibniz. Okay, so you can add on these kinds of assumptions. There's a similar assumption for your transformations. When the map that models them don't depend on when there's some details here that don't change the map, they should be represented by the same conditional probabilities. Similarly for the measurements. And all these are usually called generalized non-contextuality, which Czaslaw mentioned at the beginning in this paper of mine. And ultimately, non-contextuality in this approach is just a kind of application of Leibniz's principle. So you can get constraints from this, and you can show that for certain kinds of experiments, quantum theory violates those constraints. So again, more ways in which quantum theory resists being cast as a classical causal model that satisfies Leibniz. So Bell's theorem, causal generalizations of Bell's theorem, quotient spectra theorem, all variants of it. These are all examples of the tension between this notion of scientific realism I want, the Leibnizian principle together with Reichenbach, and what quantum theory actually says. Okay, so as I mentioned earlier, we have this way out, which is, okay, we're going to abandon this framework that models the unobserved things as variables and models our knowledge as by classical probability theory to try to get consistency between these principles and what we see. So there's two arguments that you can make now for why the epistemic view of quantum states is necessary to make this program work. So I'm going to go over each very, very quickly. So the first sort of argument is that although you can't, there's all these no-go theorems which apply, to quantum experiments. There are certain parts of quantum theory where the no-go theorems don't run, right? So I'm going to call these fragments of quantum theory. They're subsets of all the preparations, transformations, and measurements you can do. And in those parts of quantum theory, these no-go theorems don't work. You don't have the resources to go them. And what you find is that in those parts of quantum theory, you can satisfy Leibniz's principle just using this framework of classical causal models I told you about. And in those models, the quantum state always comes out as epistemic. Okay? So let me give you one example. Let's get that. If you take a particle that can, so it's just a non-relativistic particle, there's something called the Wigner representation of the states and the measurements on that particle. It's not really important how to define it. These are the definitions. The important thing is that it maps density operators, quantum states of that particle, to functions over phase space. All right, and it maps measurements also to functions over phase space. And some of the time, those functions are normalized the right way to be like a probability distribution, and the representations of measurements are normalized the right way to be like the kind of thing you would see in a causal model. And furthermore, sometimes these functions come out positive, and so I can really interpret these things as just probabilities. So for example, and I can recover the quantum statistics. So here's some examples. If I have a position eigenstate, it gets represented in the Wigner representation as something that's a delta function along position and uniform along momentum. So the interpretation then is, this is a state of knowledge where I know position exactly, but I'm uncertain of momentum. So there's a reality associated with the particle. It really has a momentum. I just don't know. That's what a position eigenstate is. I've resolved my uncertainty about position, but I've failed to resolve my uncertainty about momentum. And similarly, if I have a momentum eigenstate in this model, it gets represented as I know everything about momentum and nothing about position. And then there's other eigenstates of other quadratures that are just distributions like this one. In the measurements, it's similar. I can have a measurement which teaches me what the position was and teaches me nothing about the momentum. Other measurements that teach me everything about the momentum and nothing about the position. So these are how the quantum states and measurements are represented in the Wigner representation. You can do the same thing with transformations. There's a Wigner representation of those. The details aren't so important. The point is that they get represented by something that looks like a conditional probability from a phase space to a phase space. And in particular, if I look at unitaries, like there are unitaries that will shift position and shift momentum, they just get represented as actual shifts of the physical state in the phase space. And there's other unitaries that get represented as rotations in this phase space. So in this model, they're just transformations you can do on the physical state underlying your state of knowledge. And then finally, for composite systems, there's a way of representing them just on a larger phase space. So you have a phase space for your first particle, a phase space for your second particle. And for instance, if I take the original Einstein-Podolsky-Rosen entangled state, which is a joint eigenstate of the difference of the position operators and the sum of the momentum operators, it gets represented as just a state of knowledge where you know everything about the relative positions of the two particles, and you know everything about the sum of their momenta, but there are two other variables, like the sum of their positions and the difference of their momenta, where you know nothing. And so again, an entangled state in this model just comes back as you know 2 out of 4 of the canonical coordinates you would need to locate this particle in the 4-dimensional phase space in which it lives. And it just so happens that the 2 coordinates you know are about global properties, not local properties. When you know local properties, then you have a product quantum state. But here you know something about correlations between the 2 particles. Okay, so if you ask what is the largest set of preparations, measurements, transformations on a non-relativistic particle, such that I can get a Wigner representation that's everywhere positive, that's called Gaussian quantum mechanics. It's a fragment of the whole theory. I like to call them Clifford subtheories because the group of transformations corresponds to the Clifford group. And there's discrete analogs of this, right? So there's a Clifford group for odd prime-dimensional, collections of odd prime-dimensional systems. And you can do the same thing. You can define a Wigner function, you get a positive representation of all of it. So there's lots of different systems where you have this fragment that admits of these positive Wigner representation, and those things are Leibnizian causal models, right? They're exactly what we were looking for. They're Leibnizian because they depend only on the density operator or the transformation that you've done. They depend only on how you've represented the quantum formalism, nothing else. And they're classical because these distributions are all just probability distributions. Okay, so, if I go to my steering experiment, if I prepare the EPR state, I've prepared this correlated state of knowledge. Then if I come along and measure A, it just teaches me what the position of B was. So the idea is that if I look at the marginal distribution on B originally, it's just a uniform distribution over the position and momentum of B. Because this state of knowledge, although it tells me everything about the relations, it tells me nothing about the local property. So I start out knowing nothing. But if I learn where A is, and I know that they're perfectly correlated, I update my knowledge of B. So all that's happening here is I'm learning where B was by measuring where A is. And if I choose instead to measure the momentum at A, well, then I just resolve my uncertainty about the momentum of the distant particle. All along, the particle sits at the intersection of these two lines, and I'm just updating my knowledge about it in one of two ways. Okay, so just like the cartoon version I gave you before, here it's implemented as an actual, valid mathematical representation of Gaussian quantum mechanics. All right, it's not a cartoon anymore. This is just all rigorous. So what it says is that there's these special fragments of quantum theory. I've showed you how they manage to reproduce, for example, this collapse phenomena. But actually, Gaussian quantum mechanics has most of the stuff that we think is mysterious about quantum theory. It's got entangled states in it, it's got superposition, interference phenomena, teleportation protocol, no cloning theorem, Q distribution, almost anything that you can point to as a kind of just basic quantum phenomena, it's there already in Gaussian quantum mechanics. What Gaussian quantum mechanics doesn't have is the resources to run Bell's theorem, or the Cauchy-Specker theorem, or universal quantum computation. So those things come out as things that you can't model with these Leibnizian classical causal models. So all the rest of quantum theory that's outside these fragments, you can't do it that way. So that's the place where we're going to need to be innovative about how we represent our states of knowledge. So here, I can get away with a classical model of my knowledge and of reality. But here, I'm going to have to do something more interesting. So this is the place where I can just use probability distributions. Here, I need something more exotic. Okay. So the first argument is basically, for people who don't follow this program, my challenge is, why is it that we have an interpretation of these fragments that's so natural in the sense that it obeys Leibniz's principle and Reichenbach's principle, and we're in quantum states or epistemic? If you try to make quantum states ontic, it doesn't work. You have to give up either on Reichenbach or Leibniz. How could that be in these fragments if outside they were not the same category of thing? So the argument is that quantum states are in the category of descriptions of our knowledge. Some parts of quantum theory, I can describe my knowledge in a very conventional way, just using classical probability theory. Other places, I'm going to have to be more exotic. But how could it be that the category of this thing changes when I go from these fragments to the rest of quantum theory? If the quantum state is really ontic, then it would have to be ontic everywhere, including in these fragments. And then why is it that we have these models that satisfy these deep principles, and yet where the quantum state is not ontic? That's the challenge. Okay, and then to finish up, let me give you the top-down argument, which is still sort of a research program now. So I want to generalize this framework of classical causal models to quantum causal models, where the quantum states are going to be epistemic. And I want to convince you that although it's still a research program, there's some good prospects for doing this and salvaging both of these principles that I described. So you've already seen this slide, and so I basically want to tell you a little bit more about how this works and what remains to be done. Okay, so if you look at this paper, for example, we basically set up a framework for causal models where we derive the fact that you have to have this commutation relation for the analogs of your conditional probabilities. And we have a nice analog of what it means to be a common cause in these sorts of approaches. And that's fine, but that's not enough, because we want to argue that in these approaches, the status of these mathematical objects is the same as over here. They quantify the degrees of beliefs of rational agents. And so if I want to stick with that interpretation, then I should be able, in this new formalism, to think about these Bell-type experiments in the way that we described earlier, that learning X and S over here allows me to update my information about B, which allows me to update my information about Y. That if this were all described by a classical causal model, then I can always update my knowledge in a sequence. I can say, what does X and S teach me about A? What does A teach me about B? What does B teach me about Y and T? I can do that sequence of updates. So let me show you how that works classically, right? So if I start out with some prior knowledge of D, and then I condition on the values of X and S, well, what's given in the problem is some joint distribution on A and B. That's, just my knowledge of the source tells me how A and B were correlated. So that's encoded here. And I have some description of the measurement, which is a conditional of x given a and s. So the first thing I want to do is say, all right, what do x and s teach me about a? So now I have to do a Bayesian inversion. So the first step is say, okay, I want to know what I learned about a given s and x. So I take x given a and s, I multiply by the marginal on a, I divide by the conditional x given s. That's the usual formula for Bayesian inversion that will allow me to compute my new beliefs about a when I register the values of x and s. That's step one. Next step, given that new knowledge of a, what should my new knowledge of b be? So the first thing I'm going to do is start with this joint on a and b and turn it into a conditional, b given a. So that allows me to, for new information about a, update my beliefs about b. So that's just the standard formula in classical probability theory for computing a conditional probability from a joint probability. And then I just combine this conditional with this one using the following formula, right? So I take my probability of a given s and x, multiply my probability of b given a, sum over a, and I get my new knowledge of b given s and x. So this is just a standard calculation in classical probability theory that is one way I could update my knowledge. So the claim is if you think that quantum states have the same status as I do, as these conditional probabilities, then I should be able to do exactly the same thing in my quantum model. If I want to think of the update of the quantum state of B as a transition from my initial state of knowledge of B, which is represented by this operator, to some new state of knowledge of B, which is represented by this set of operators, then I need to have the analog of all these formulas. So what's given is a joint state on AB, typically entangled, a characterization of this measurement over here, which is given by one of these operators, x given SA. And I need some formula for Bayesian inversion. So I need in this formalism to have a way of computing what I should believe about A given x and s in terms of the things that are given in the problem. I have a paper where we suggest a way of doing this. It involves a particular kind of operator product, which is non-commutative, non-associative, and I'm not going to go into the details of it. You can look at the paper if you want, but this is what the star means. This inverse means I'm taking the inverse of this density operator on its Hilbert space support. So this formula is written in a way to make it look exactly like the Bayesian inversion formula, where the product is being replaced by this special new operator product. You need a formula that's the analog of computing a conditional from a joint. So again, the star product gives us a way of computing that thing. And you finally need a formula for propagating your beliefs, where here this summation over A is replaced by a trace operation. And this is the normal product. So we have a formalism with this special star product that gives you analogs of all this, and it allows you to do your calculation this way, updating through A and B, and it gives the right results, right? So it allows you to update your knowledge about the outcomes of distant measurements, given the measurements of this guy here. So that's great. The problem is I can find other experiments where the formalism we wrote down is not adequate. Okay, so this formalism can't be the final story. So this is the main paper with Matt Leifer, where you'll see this formalism described. It builds on previous work by Matt and David Poulin. And in some recent work with co-authors, we show, we were already, in this paper, we already talked about some of the limitations, and here we kind of expand on the limitations. So this is not a formalism that will work in general. But I presented it to you to give you a flavor for what has to be done, right? Like if this could be made to work regardless of the causal structure of the experiment, if there was a formalism that could tell you exactly how you must update your knowledge in a way that respects that causal structure, then we could say, we've done it, we've recast quantum causal models where we clearly separate what's about causal relations and what's merely about our knowledge. But as I say, it's not done yet. It's still a work in progress. Okay, so let me sum up. So we have this interesting situation where you've got these parts of quantum theory, like Gaussian quantum mechanics, or the stabilizer formalism for qubits, or the stabilizer formalism for any odd prime dimensional system. And in those parts of quantum theory, you can represent everything there using a Wigner-like representation, and you get just a classical causal model for what's going on. It satisfies Leibniz's principle, and quantum states correspond in those models to states of incomplete knowledge of some reality. The idea of these models is that you can never resolve your uncertainty completely. You always are limited in how much you can know. You can know position, or you can know momentum. You can't know both. But the formalism of quantum theory is all about sort of keeping track of your limited knowledge and how you transform it from one form to another. But we also have these no-go theorems, which say that outside of those fragments, right, so if I have greater quantum resources, I know that these kinds of classical causal models don't work. I cannot represent all my procedures just using probability theory. But because we don't want to give up on scientific realism, formalized through Reichenbach's principle, and I think we should not give up on Leibniz's principle either, it seems to me that the approach for dealing with the rest of it is to say classical probability theory only works in limited contexts, and the formalism for how we ought to reason about systems and how we ought to propagate our beliefs about one system to another system, that formalism doesn't have to be classical probability theory. I like to think about classical probability theory as not a priori. It's not as if we can sit in an armchair and deduce what is the right formalism to model our incomplete information. I would rather think of it as empirical. What does probability theory do for us? It allows us to survive well in the world. It's an adaptation. We actually, I believe, there's a certain level of sort of Bayesian filtering going on in the unconscious neural networks in our head, like the spam filters in email. Those use principles of Bayesian inference. They're adaptive. And it can be that in situations where you need to reason about systems that are not behaving classically, but quantumly, that the most adaptive theory of inference for you to use is not classical probability theory, it's something else. And the idea is that if we can sort out what that is, then we can interpret the quantum formalism as being essentially this new theory of inference. Good, so that's the picture. Let me end with one analogy. So in anticipation of people not feeling the force of this argument, I'd like to point out a nice analogy. Actually, do I have time for one more analogy? Yeah? I'm at an hour and a half now, yes? No, that's good. Okay. So the analogy is to the decipherment of Egyptian hieroglyphs. So this is my favorite example of an instance in science where progress was impeded by a category mistake, where people just got the nature of something wrong. So I think that's what's going on in quantum theory. So my own analysis of why is it that there's so little consensus on what the interpretation of quantum theory ought to be, even though we've had it for so long. In other realms of physics, you tend to develop a scientific consensus about how to make sense of the theory. Why hasn't that happened in quantum theory? And I think the answer is because we don't yet have the correct interpretation. We have this kind of instrumental interpretation, which allows us to compute statistics. It doesn't provide a causal account, so we're missing something. We're missing the causal account. And the reason we haven't got the right causal account is that thus far most people have been focused on interpretations that treat the quantum state as a description of reality. And so I contend that that's a category mistake. That's just getting the nature of the quantum state totally wrong. It's not a description of reality, it's a description of our knowledge of reality. And when you've made a category mistake, that's disastrous because everything you try to do is under the lens of that mistake, and all the questions you ask are kind of wrong-headed. So that's what happened with hieroglyphs. So in the case of hieroglyphs, it was around 500 AD that the last person who could read and write hieroglyphs died. And then it took 1,300 years before it was deciphered. And the reason was that people assumed that they were ideograms. So they thought that hieroglyphs, the particular glyphs, represented ideas directly, not through any spoken language. So that they were like signs in an airport, where it's meant to be, no matter what language you speak, you'll understand the meaning of this sign because it sort of depicts a concept directly through an image. So everybody presumed that this is how we were to interpret hieroglyphs, that they were a kind of ideographic writing system that had like a kind of symbolic meaning for every one of the signs. And people wrote textbooks about what hieroglyphs meant under that interpretation, right? There was serious work done under that interpretation trying to make sense of things. 1799, they discovered the Rosetta Stone, which had hieroglyphic writing and Greek alphabetic writing, the same message in both writing systems. The middle one was called Demotic, which turned out to be a cursive form of hieroglyphs that was developed later. So they discovered this. They knew how to, Greek was still spoken and written, so they knew exactly what this edict said. And they were quite certain that the hieroglyphs had exactly the same message. Now, it took 23 years after the discovery of the Rosetta Stone to decipher hieroglyphs. Because it's a bit like the situation in quantum theory. You now know exactly what this says. There's no question about that. Much like the quantum formalism allows us to compute the statistics of measurement outcomes. So what I was asking is, we want more. We want a causal account of those. Here, what you want is, how do the hieroglyphs manage to say that? It's nice and well to say that the hieroglyphs here say this. But how do they manage to do it? What's the particular glyph by glyph interpretation of hieroglyphs such that I can extract this message from the hieroglyphs? That's what people were looking for. That's what a decipherment consists of. So the progress was made some years after the Rosetta Stone discovery. People noticed that there was these special cartouches in the hieroglyphs that were circled by these loops. And they got the idea that they knew that the names of various rulers appeared in the Greek text, like Ptolemy's name, who was the ruler at the time this was made, it appears like 11 times, and Alexander and Alexandria appear in here. And so they thought, okay, maybe these cartouches are the names of pharaohs and rulers. And Thomas Young, the interference pattern Thomas Young, realized that he could make a phonetic interpretation of the symbols inside those cartouches that would sound out the name of Ptolemy, which, because we know how the Greeks would have said it, we know what it would have sounded like. So from that point on, people realized, yes, that seems right. So the guy who eventually deciphered it, a Frenchman by the name of Champollion, realized that if you took the phonetic values that was suggested by this hypothesis, that this was spelling out the name of Ptolemy, and you took those phonetic values to other bits of hieroglyphs, he could reconstruct Cleopatra's name, or something like it, for other inscriptions that had Greek counterparts. And he knew Cleopatra's name appeared in the Greek, and he could decipher it with his phonetic values. So he managed to get more phonetic values. He found names of other pharaohs, even ancient pharaohs. So all of a sudden he had, all the cartouches kind of made sense under a phonetic reading of the hieroglyphs. So phonetic is a completely different category from an ideographic reading. An ideogram represents things independently of spoken language. A phonetic representation means that the glyphs represent, the phonemes of a language, either the sound of a word, or the sound of a syllable, or the sound of a consonant or a vowel. So they had that now for the cartouches. And amazingly, they decided that was only true for the cartouches and not the rest. So they thought, oh no, the rest of it, that's got to be ideographic. And so they still tried to sort it out. And so finally, Champollion, one day, decides he's going to see what happens if he takes this phonetic reading of the glyphs and apply it to the rest. And if it had been the case that the language spoken by the Egyptians hadn't survived to his time in any form, then this would not have worked, right? Because it's a spoken language. It's the sound of a spoken language. But so it turned out that the language of the Egyptians had died out as an everyday spoken language around the time where it was conquered by the Arabs, and Arabic took over as the language spoken by the Egyptians. But prior to that, the Egyptian language had been incorporated into the Coptic Christian church's ceremonies, and so there was this liturgical tradition in the Coptic Christian church where everything was still done in the language of the ancient Egyptians, and that language came to be known as Coptic. And it just happened that Champollion had studied Coptic. That was one of the languages he was familiar with. So when he tried his phonetic table on the rest of the hieroglyphs, he started seeing the nouns and the pronouns and the grammatical constructions of this language he knew, which was Coptic. And that was like his eureka moment. Like at that point, he realized he had it. He deciphered hieroglyphs. And when he took all that and built on it, he was able to reconstruct the Greek message from the hieroglyphs. And then it was clear it's all phonetic. And none of these glyphs are ideograms. So that's the analogy. If we've got this interpretation of the Clifford fragments, those are like the cartouches. The quantum state is epistemic in that interpretation. This interpretation gives us causal explanations. It does it in a way that reproduces Leibniz's principle. The alternatives, like Bohmian mechanics, does not do this. It involves superluminal causal influences, which are non-Leibnizian. But the price of having those interpretations is that the quantum states have to be states of knowledge. That's the category thing a quantum state is. Now, if somebody postulates that the category of the quantum state changes when I leave that, that's like saying the cartouches are phonetic and everything else is ideographic. One, doesn't make a lot of sense. Two, you kind of need to give a reason. The people who were deciphering Egyptian had a reason. They thought, well, proper names are special. These are foreign names. People would have to spell out phonetically what foreign names would sound like. And so that's why there's this special exception. And even after Champollion discovered that the names of ancient pharaohs were still spelled out phonetically, he still made this special exception. He said, well, maybe it's just proper names that are spelled phonetically. But they had a reason. They had a story for why it could be ideographic everywhere except these cartouches. And I feel like the opponents of the epistemic view of quantum states have yet to provide me with any kind of story that would tell me why it is that even though quantum states are everywhere ontic, nonetheless, in these special fragments, I can have these interpretations that respect Reichenbach's principle, respect Leibniz's principle, if that is fundamentally flawed. I would like to know why is it that nature has deceived me in this way to think that quantum states are epistemic when really they're ontic. And so that's sort of my challenge to those who believe that quantum states are real. Provide me with an explanation for why it works so well in those fragments of quantum theory. So with that, let me just leave you with some references. Thanks.
Please, feel free to ask questions.
Okay, yeah, so I have a question. It comes to the PDR theorem.
Yes.
So, a priori, it would seem that it might be a challenge to this interpretation. So basically, I guess it says, well, it's an argument against the epistemic view, saying that, I don't know, if the most essential assumptions are, I don't know, if you have independent measurements that at the epistemic level, that the ontic states should also be independent or something like this. And this somehow would call for a causal explanation along the lines of what you were doing. Can one say that, that it's in conflict of, I don't know, the Leibniz Reichenbach principle? I don't know, maybe.
I just need to find an eraser or maybe before.
So does it require fine-tuning in your setting?
So, let me put it this way. There's a set of assumptions that look a lot like the PBR assumptions, which I'll call separability and preparation independence. And I think these are both natural assumptions, and in particular, preparation independence is an example of preparation non-contextuality, and therefore it is a Leibnizian principle. And separability is a very natural. So what a separability means, it means that if I look at a composite system A and B, and this describes the space of all ontic states on A and B, then that's just the Cartesian product of the set of ontic states on A with the set of ontic states on B. So separability is basically saying there's no holistic properties. When you tell me the physical state of A and the physical state of B, you've told me everything about the physical state of the composite A, B. Okay, so I think that's a very natural assumption. If you're building causal models, you've got a pair of systems, their realities are independent, there are no holistic properties. And then this is like I said. So I endorse these assumptions, and my sense is that most people who read the PBR paper think that these are the assumptions of the PBR theorem. But actually, these assumptions don't get you to the conclusion of PBR. They get you to the conclusion that there's no psi-epistemic ontological model. So in the talk I just gave, I talked about classical causal models rather than ontological models, but an ontological model is just one of these classical causal models I was talking about. And no psi-ontic ontological model. So if you start with these assumptions, all ontological models fail to reproduce what you've seen, not just the psi-epistemic one. So there's no possibility of salvaging an ontic interpretation of quantum state. So why do you rule this one out? The answer is that if, for example, if you think the quantum state is part of the description of reality, because you believe in Scientology, then when I ask, is it the case that the reality for the composite system includes more than just the reality for components? The answer is yes, because there are entangled states. Entangled states cannot be specified by specifying one state here and one state here. So if you think that entangled states are a way of being, not a way of knowing, then just the existence of entangled state already shows you that you can't have that. So you don't need to appeal to this assumption. Boom, you can't have it, you're done, it's trivial. If you want to show that psi-epistemic models can't satisfy the assumptions, you've got work to do. You have to look through the PBR construction and prove it. So from my perspective, if the PBR paper had been written this way, I would have said, well, it's very much like Bell's theorem and the quotient spectra theorem. It rules out all ontological models, regardless of how you interpret the quantum state, and it's based on natural assumptions. It's just that it doesn't start from this assumption. It starts from a different assumption, which says there are holistic properties, but those holistic properties only get populated if you've prepared an entangled state. Now, what I don't like about that assumption is this is supposed to be a theorem that's meant to convince me to be psiontic, not psi-epistemic. So it's a bad thing if it relies already on psiontic assumptions. So if somebody says to you, I've got an idea that maybe we need holistic properties only for entangled states, that sounds reasonable. Why does that sound reasonable? Because we're so accustomed to thinking of quantum states as ways of being, and an entangled state is a fancy way for things to be connected. But if I'm a psi-epistemicist, I don't think of entangled states that way. Entangled states are just a way of knowing about two objects, and there's no reason to think that there should be any holistic properties associated with them. So for my money, it's fine to assume separability, but to assume it only for product quantum states and not assume it for entangled states is a totally unnatural assumption. It already relies on psiontic intuitions, and so it doesn't persuade me at all. And the other thing is that it's kind of ironic in a way, because the same sort of thing happened with Bell's theorem. That, from my perspective, Bell's theorem has the following sort of history. Einstein recognized the distinction between psiontic and psi-epistemic ontological models, and in 1935 he showed if you want to preserve locality, you have to go psi-epistemic. Essentially, the cartoon argument I gave you is Einstein's argument for why you have to go psi-epistemic. And then in 1964, Bell showed even if you go psi-epistemic, you still can't salvage locality. So it was easy to rule out locality for psiontic models, hard to rule out locality for psi-epistemic models, but at the end, it's ruled out for both kinds. You have to do something else. And yet today, we find, ironically, a lot of physicists saying, Bell's theorem proves that the quantum state's a complete description of reality. That's an ironic mistake because it gets it backwards. No, that's the thing that was easy to rule out. That's what we had ruled out from 1935 onwards. It's, what Bell's theorem does not establish that we go back to thinking of the quantum state as a complete description of reality. So it's similar here that when people point to PBR and say it rules out psiontic, often they don't appreciate the distinction between this assumption and this other assumption I told you. And if so, then they're making this ironic mistake because they're claiming that we should go back to something which is actually trivial to rule out under this assumption. And the thing that's hard to rule out under this assumption is this one. But at the end of the day, if you take this version, I would say, yeah, it's a nice theorem. I can add it to the list of Bell's theorem, the quotient spectra theorem, and so forth. We have a whole diversity of them. And they all prove the same thing, which is that there's something wrong with the framework, because that framework doesn't allow us to hold on to causal explanations and Leibniz's principle, and so we should abandon that framework.
Comments, other questions?
Sorry. You had one transparency, I think, if I reproduce this correctly, if you want to obey Leibniz rule,
Yeah.
and S is a cause implies superluminal. Implies signaling, or can you go back?
Yeah, I can go back to that. This one?
Yeah, and the negation of that, you have an M, but this is first okay. I wasn't sure about that, so my questions are different now, because I wasn't sure about that.
Okay.
So, at some point you said that you would like to consider causal structures fundamental. Now, I want to hear your opinion. Since the causal relations are, after all, placing events in space-time, connecting them through the wires, And if there is a possibility to even these wires,
so what's that word?
Even these wires, if it's a
wires,
if there is
okay.
it's possible these causal relations, which are physically represented after all through wires and placed in the laboratories in space-time, if they are also controlled by quantum states.
Mm-hmm.
And quantum states could be, for example, entangled
Mm-hmm.
and put in a Bell's theorem. Like, is this a way to weaken even this notion of kind of objectivity to the causal structures? Or you think that after all, because they are quantum states that will control them, they should also be somehow embedded in space-time and therefore have some causal structure which is a definite?
So, suppose we could find examples of this within the Clifford fragments of quantum theory. So the kind of thing you're talking about, where maybe some aspect of the causal structure will be determined by the quantum state of something. So in this causal models framework that the statisticians use, there's already the opportunity to kind of have dynamical changes of causal structure because, for example, I could make something like this. I could say either A is going to cause C or B is going to cause C. And the way I do it is by having a new variable, which I'll call a switch variable J, and then I say something like C is going to be just equal to A when J is 0, and it's going to be equal to B when J is 1, for instance. So that's a way in which I could kind of encode a path-dependent causal structure just in the Dirac formalism, right? So I have to include both arrows as the fundamental causal structure, but what the particular form of this dependence tells me is that depending on the value of J, only one of them is really acting at any given time. So I can implement some dynamics of the causal structure just within this framework, okay? Now, if in such a framework, so we say we're in one of these Clifford fragments, and now I say this switch variable is put into a quantum state, well, that quantum state only represents a state of ignorance about what the underlying state of that variable is. So what it's going to mean is that I'm going to have ignorance about whether A is the one that has the non-trivial influence on C, or B is the one that has the non-trivial influence on C. So there's not going to be any indefiniteness in the causal structure. There's just going to be epistemic ignorance about what causal structure is going on.
Even if the J's are entangled?
Yes, because even entangled states in these Clifford fragments are just ways of knowing about two systems which have properties of their own, and it's just correlated knowledge of the two. So even entangled states don't involve any kind of weird holistic properties. They're just ways of knowing. Okay, so now if you go outside Clifford, you don't have that way of representing quantum states as probability distributions. But if the research program I described could work, then I expect what's going to happen is that it'll be something similar. It'll say, when I make causal structures dependent on quantum states, that corresponds to having a state of incomplete knowledge about the causal structure, but it's a state of incomplete knowledge that cannot be represented by a probability distribution, it's represented in some other way. And I can't quite see exactly what it'll look like, but I suspect it'll have more the flavor of, well, the causal structure is not indefinite. It's just that you have restricted information about it, and the restriction on your information is one of this sort of weird type that can't easily be described by probability distributions. So it's hard to predict what would happen in that final theory that did it, but if I had to guess, it would be something like that.
So you will stick this class. I just wanted to know your opinion. I know that this is somehow yet to be investigated, but you will stick to objectivity of the causal structures. Am I right? Even relaxing the model, saying this is not classical probability, these are states, but you will stick to it.
Well, so far, none of the no-go theorems that I'm aware of force me to stop being conservative about the causal structure. Like, as far as I know, I can take a very plain vanilla causal structures are just DAGs approach to interpreting quantum theory, and it could just work, right? I just have to innovate how we formalize our incomplete information, and it'll be fine. Now, it's possible that as this research program develops, there'll be some new no-go theorems that say, actually, that idea that you can be conservative about the causal structure and put all the radical elements into your state of knowledge, maybe that's going to give. So maybe, somehow this fact that I can make the causal structure dependent on a variable, I don't know, it looks like it should be consistent with being conservative about the causal structure, but maybe it breaks. And so, it's possible that in the future I will answer that question differently. I'm just saying for now I don't see a reason.
So my question is more or less closely related because, so as far as I understand, you would, let's say, assign a nontic interpretation to the causal structure only, or at least to that, right? So my questions would be, well, first of all, if there is anything quantitative that one can say, like about something quantitative but also ontic about nature, and also, so about this thing that the causal structure might be non-well-defined in some cases, I would also put the example of, so how does it agree then with general relativity that in total generality one would also lead to not well-defined causal structure in the sense that you could have something like closed time-like rules or something like that, in which, so I mean there is a problem of causality also in other theories that we know that work very well. So my more general question would be how the, let's say, symmetries that we say in nature that are also very well established, how would they enter into this framework? Would you assign some ontological meaning to them, or is like a secondary thing?
Did you say symmetries?
Yes, or like something like the special relativity interpreted as the Lorentzian symmetry, for example, that is something that is ontologically real with respect to the causal structure that might arise from that thing.
Okay, so general relativity. So it's if you look at the solutions to general relativity that involve closed time-like curves, then clearly those types of solutions can't be modeled by a directed acyclic graph because they have cycles. But my understanding is that, well, I mean, the first thing you can say about it is that if I allow a cycle and I don't put any further constraints, then I can set up logical contradictions, right? I can set up a loop where, I do a NOT gate so that something that was 0 has to be 1 and I get a strict contradiction. So any theory that posits cycles without extra constraints can be ruled out on grounds of logical inconsistency, which I think are the strongest grounds possible for ruling out a theory. And in particular, for example, David Deutsch's work on setting up causal loops in quantum theory, if you take those proposals and you interpret the quantum state epistemically, as I've suggested, they also involve a contradiction, because if I have a quantum state that's in the completely mixed state, and it goes through a NOT gate and comes back as a completely mixed state, you might say, no contradiction. But if your interpretation of the completely mixed state is, I just don't know whether it's 0 or 1. So deep down, it's 0 or 1, it goes through a loop, it gets knotted, and it contradicts itself. And the fact that I happen to assign a uniform distribution over 0, 1 doesn't save the theory from contradiction. There's still, according to the theory, a contradiction at the ontic level. So my epistemic reading of those proposals says these actually do have grandfather paradoxes in them. And it's only if you interpret the quantum state ontically, if you mistakenly interpret the quantum state ontically, in my point of view, that they look like they save themselves from contradiction. So I'm not an expert on closed time-like curves and solutions to general relativity, but perhaps they also really involve a contradiction, or maybe they're not solutions that are actually realized in reality. So it's conceivable that general relativity is consistent with this DAG framework because it doesn't actually involve loops. So again, like in answer to Chazov's question, I don't really see any reasons that physics requires us to allow for causal loops. Like if maybe there's in the future somebody can persuade me that physics has to incorporate causal loops, and then we're going to need a more general framework, but for the time being, I don't think we need them. Your last question about Lorentz symmetry. So I like to think of Lorentz symmetry as somewhat a kind of a choice of coordinate system. So it is a bit of an epistemic thing. It's sort of, you can describe things in many different ways, these different coordinate systems. And ultimately, you would like to have your ontology be something that can be described in some fixed way, which then looks different from different points of view. And special relativity does achieve that. So if I think of a meter stick or something as its whole world tube, right, then I can make sense of the fact that one observer measures it with length L, and another observer that's moving at some velocity with respect to the first measures it as length L prime. I can look at that and say that's not a logical contradiction, because what we have is this world tube, and observer 1 is measuring this slice of it, and observer 2 is measuring this slice of it, and so they're measuring different things. There's not this one monolithic thing of the length of the meter stick. There's the length of different slices through the world tube of the meter stick. And so in special relativity, I think we do have a good sense of an objective reality, and all the different reference frames just have different epistemic access to that objective reality. So I don't know if that answers your question.
Well, my question would have been whether in a hierarchy between causal relations and symmetries, which one is more fundamental? This was like short, make it short. Yeah, because let's say to also justify why I made it, because I thought that one could ultimately hope to have some quantitative, let's say, notion of something real, right? And then a causal relation to me looks only like a qualitative relationship between parts. While if I have a symmetry, I can say that there is something which, I don't know, for example, is conserved during, so it's something that it's conserved during, or can be reasonably thought to be a constant of nature or something like this. And that would be to look to me more fundamental with respect.
Okay, well, I didn't need it for the purposes of this talk, but if you ask what are all the things that could be assigned ontological status in the classical causal models framework. So one thing you can do is you can say, rather than having a DAG together with some conditional probabilities, you can kind of do the analog of dilation that we do in quantum mechanics. You can say every time I have a indeterministic dependence, some conditional probability that's not deterministic, I'll understand that as really there's some other variable that influences, and I just have ignorance of it. So I can, so if B depends on A probabilistically, I can say, well, that's because B doesn't depend only on A. B depends on A and some other stuff, and it depends deterministically on that, and I just fail to know the value of the other stuff. So if I write down that kind of causal model, where I insist that for every variable, all of its causes are included in the model, then the parameters just become functional dependencies. So I can write the effect as a polynomial of all its causes, and the values in that polynomial specify the precise strength of the causal connection. And so in that way of approaching things, the parameters would be also ontological. Now, you'll notice that in my slides, I didn't stop on this, but I called those parameters causal statistical parameters. So it's kind of a hybrid of ontological and epistemic things. That's because the way I did it, those conditional probabilities are a kind of Frankenstein monster of two things, because they fold together the functional dependencies, which are ontological, with your lack of information about those systems, and so they're not cleanly one or the other. So it is actually better to insist on your causal model being one of these dilated kinds, where all the parameters are ontological, and then you can separately specify what you know about each of these variables, and then you have this really clean distinction. It's just that for the purposes of this kind of talk, it kind of is just too much formalism and it confuses things. But yeah, it's a better way to do it.
Question concerning the conditional probabilities, actually. I've always wondered, because in the mathematical context, it's not linked to any time frame, actually, the conditional probability. But now, and in both applications, even with this one, it means that the conditions comes before the next one. Okay? So in some kind of context, do you have any issue on this before and after, or is this not playing any role? Because there are definitions of time-like processes which are defined by causality, and on the other hand, causality is defined by a time-like before and after. And isn't this a kind of circle? Or?
So, have thought about this. So I think what's confusing about discussing temporal ordering in probability theory is that there are sort of two distinct temporal orderings. So there's the temporal ordering in the world, so it's sort of an ontological temporal ordering. So maybe I have, for example, a quantums or a classical system A that comes into a device and a system B that gets spit out, and maybe some outcome X.
So A is before B.
Yeah, so yeah, and time is going this way. Okay? So these are all existing in the real world. Now, I, as an agent, can ask a number of questions. I can say, how should I update my knowledge of A when I learn that X has some particular value? How should I update my knowledge about B when I learn that X takes some particular value, for instance? The idea is there's not necessarily any, like here, I'm learning about the past based on something that came before. That's fine. Conditional probabilities do not require you to be making inferences about the future. When
I'm speaking of the past.
Sorry, but they don't.
I'm speaking of the past.
Sorry?
I'm speaking of the past.
Exactly. So I dig in the ground, I find some bones.
Yeah.
It looks like a T-Rex.
Yeah.
I assign a higher probability to the proposition that 1 million years ago, dinosaurs roamed the Earth. I have updated my conditional probability about a fact in the past based on evidence in the present. That doesn't mean that my uncovering these bones had a causal influence on the past. It's just that inference doesn't work that way. Inference doesn't care whether the connection is by virtue of a common cause, A causes B, B causes A. All those scenarios can serve as bases for inference. The evidence and the hypothesis that you're updating your knowledge about can have any causal relationship with one another. So there's nothing about the formalism of classical probability theory that cares about the causal relationship between the things you're conditioning on and the things that you're updating your knowledge about.
But if I cannot distinguish which was before and which was after, can I use conditional probability at all?
Yes, well, I'm not sure exactly what you're asking me to hypothesize, but the claim here is that, much like when I described Simpson's paradox, if we are not careful to make a conceptual divide between the causal structure and the purely inferential structure, what teaches me about what else, if we're not careful in our formalism to separate those, we can get into all kinds of confusions. So similarly here, if we're not careful to speak about the following distinctions, what's A before B in time versus in what order did I learn certain information, right? So,
yeah, but this order is in time, isn't it?
So for example, let me give you a contrast. I might want to update my knowledge about A or B based on X. I might want to update my knowledge about A or B based on Y. Okay? It could happen, for example, that somebody did this experiment, they told me the outcome X first, and then they told me Y. So maybe I would update my knowledge about A in a two-step procedure. First I learned X, that taught me a bit about A. Then I learned Y, that taught me a bit about A. So there's a temporal ordering of the data I got. That's sort of an epistemological timeline. I learned this at that time, I learned this at that time, and so forth. That temporal ordering has nothing to do with the causal ordering of the systems in space-time. I have a hypothesis about how they're ordered, and I can use classical probability meaningfully to update my knowledge based on that causal structure. But as soon as we start confusing the temporal order in which I learn some data with the temporal order of events in the world, and we don't make that distinction, then we're going to get into all kinds of trouble. And we're going to think things like, doesn't this have to happen before that? No.
Yeah. Just for myself, this kind of conditional probability is actually linked to the natural process of learning about something, where something comes before the thing, and then afterwards you learn something about. Is this correct, or is this wrong?
Well, in my dinosaur example, I update my knowledge about the past based on evidence I have in the present. So I think conditional probabilities can be used to update your knowledge and the temporal relation between the two propositions we're talking about, the temporal relation between, there's a temporal relation that's induced by the causal relation. So in the model of causation I'm using, causes only propagate forward in time. So the point I'm making is that conditional probability is causally neutral. It says, I give you two events. How should you describe your ignorance of them? Use a joint probability distribution. Classical probability theory doesn't say, oh, use a joint distribution if A is before B and use something else if B is before A. Classical probability theory says, I don't care how A and B are related in space-time. If you want to describe your ignorance of A and B, you always use a joint distribution. How do you update your knowledge? If you get new information about A, here's how you update your knowledge about B. Compute the conditional. Throw in your new information. Multiply it. Does it matter how A and B are related in the world? Classical probability theory says, no, it is irrelevant how A and B are related in space-time. You always use the same rules for updating. So one of the challenges of coming up with a quantum formalism, and so if you look at the title of the paper that Matt Leifer and I wrote, is it was towards a causally neutral, or formulating quantum theory as a causally neutral theory of Bayesian inference. So we thought that was inherent in a theory of inference, that it doesn't care what the causal relations between the variables that you're talking about are. And that's one of the challenges, that the quantum formalism as is normally given to us models a map from A to B as a completely positive map, whereas A and B is modeled by an entangled state, and they look like different objects. If I want to recast that formalism as inference, it's got to be exactly the same object for both scenarios, and the way I make inferences should look exactly the same. If you can't do that, then I would say that's a no-go theorem. That shows you can't do this. That I think it's inherent to probability theory that it should be general purpose, it should allow you to update your knowledge regardless of the causal structure. Because, in fact, classical probability theory doesn't even have to be talking about space-time events at all. I could say, what probability do you assign to the truth of this mathematical proposition based on the fact that I just proved this other mathematical proposition? Those propositions don't live in space-time, but we can still use Bayes' theorem and probability theory. So to my mind, they're really very different kinds of things, causal structure and the formalism of classical probability theory.
Yeah, thanks for your talk. It was really interesting. I have a question though concerning the complementary aspect of the dynamical picture that we're going to end up with on the epistemic. Namely, we have two ways of updating the state. By way of projection postulate, we have unitary dynamics. And projection postulate seems on the epistemic fairly natural. I make a measurement, I learn something about the world, and I update my belief. But how are you going to account on this epistemically for unitary dynamics? Because the intuitive idea, I guess, would be something like, I have some state of knowledge, and I have that. Why should that evolve? Why should that change in time when no measurement happens?
Okay. So, say we're talking about one of these situations that's inside one of the Clifford fragments of quantum theory. Okay, so a non-relativistic particle, here's the phase space, and suppose that my knowledge starts out as some Gaussian distribution on the space space. Okay, so that's my epistemic state initially, so that the physical state is some point in that distribution. Okay, so now suppose I apply a device which shifts. It's like a shift in position and momentum. So consider the unitary whose exponent would just be some linear function of the position observable and the momentum observable. So in the underlying ontic space, every ontic state gets shifted over. That's how you represent in the Wigner representation that unitary. So everything gets shifted over. So if I then ask myself, somebody's told me that this evolution, this physical dynamics, just happened to the particle. How should I update my knowledge? I reason as follows. Well, I assigned a certain probability to the particle being here, and you told me that it's moved here, so I assign the same probability to being here. And in the end, I say my new knowledge, my best description of where the particle is now this distribution. So the point is this, that the ontic dynamics induces a map on the space of epistemic states. And so I have a representation of the unitaries at the level of the ontic states. I also have a representation of the unitaries at the level of the epistemic states. And so the fact that quantum states evolve under unitaries, well, that's just because epistemic states evolve under dynamics just as much as ontic states do. So it doesn't pose any challenge to the epistemic view. In fact, it accommodates, like in these Clifford fragments, it makes a lot of sense. So that in the theory that Czesław mentioned, where you have a discrete system that just has a binary position variable and a binary momentum variable, and your epistemic restriction basically corresponds to knowing, say, just the position, in which case you know nothing about the momentum, or you might know just the momentum, in which case you have uniform distributions over the two possible positions, or you might have knowledge of the sum mod 2 of position momentum. So these are your 6 states of knowledge in that theory. And if I draw the simplex of all possible probability assignments to these 4 ontic states, right? So I could write all 4 of the physical possibilities. The set of all distributions of those guys lives in this simplex. These 6 guys basically are the vertices of an octahedron that lives in that space. Okay. So if I ask what are the transformations, it ends up being just all the permutations of these 4 ontic states. There's 24 such permutations in all. Those are the ontic dynamics. If I say what do those ontic dynamics, what kind of dynamics do they induce for the epistemic states? So, for example, if I have one ontic dynamics that might be this 2-cycle, what does it do to this epistemic state? Well, it maps it to this one. So I can draw that in this picture, right? Each one of these is one of these epistemic states, and I can draw what this map does here and here, and it takes this guy over to him. And if I work it out, what you find is that it looks like rotations in this space. So we know in the block sphere, unitaries are rotations. When you think of the quantum states in the block sphere as representing these epistemic states, you easily see that that's the appropriate representation of the permutation group at the level of the epistemic states. they naturally become rotations in this picture. I've left out a caveat, but anyway, that makes my point.
Can I
Yeah.
ask you? Because maybe I just don't know enough about these Clifford fragments. And
Yep.
that means I should just shut up. But I'm going to keep pushing. So, but my worry would be that this type of picture, you have to restrict yourself to Cartesian coordinates in your phase space, right? So this doesn't, because the wave function doesn't transform like a scalar field under Cartesian coordinates. Right? So this idea, you get these sort of extra terms.
So if I'm talking about non-relativistic particle mechanics,
yeah, non-relativistic, just quantum mechanics.
Yep.
Suppose quantum mechanics in polar coordinates, right?
Sorry, quantum mechanics.
Quantum mechanics in polar coordinates. We just
polar coordinates.
Yeah, we just
Okay.
quantize our phase space. Then the wave function, right? You don't really know what it means to have a wave function that is being shifted, because it doesn't have the right transformation in the mathematics. Because you destroy the self-attractive like the momentum in general without defining covariance. So that would be my worry that these sort of unitary transformations is natural relative to choice of strategic coordinates, which makes, in the epistemic sense, perhaps sense somehow that this feature of how we coordinate as well is built in fundamentally into how we interpret wave function.
So I'm not sure. I mean, if I take one of these Clifford fragments, which, for example, includes displacements in phase space, I can shift the position, shift the momentum, I can rotate, I can do all these kinds of things. But there's many other unitaries that does not allow. But if I restrict the scope to those unitaries, so strictly speaking, they're the ones that have generated by Hamiltonians that are quadratic in position momentum, then I can always represent those unitaries as an ontological dynamics on the underlying phase space, and the action on the bigger distribution is just induced from that. And even if I were to choose some strange coordinate system here, not the standard one, that would still be true. It would just be harder to prove. But the coordinate choice is just a choice of how I'm describing this. Everything would still go through. If, however, you said, let me write down a unitary which has a very simple description relative to polar coordinates, and it looks very complicated from the perspective of phase space, then I'd say, oh, that unitary doesn't live in the Clifford fragment. And so, yeah, I'm not going to be able to model that unitary here. And that's just because these Clifford fragments can't do everything, right? So that's what we need the rest of the program to solve for us, because these kinds of pictures only make sense in Clifford fragments. But to my mind, the question you started with was, I feel like you sort of, we're often tempted, I mean, I hear this question a lot, and my impression is that this is kind of what you need to see to understand that there's no obstacle to understanding unitary dynamics as acting on epistemic states, because any ontic dynamics will induce the dynamics on the epistemic state. I mean, so did I get that right? Have I persuaded you of that at least? Okay.
Thanks very much.
So I would like to hear your answers on this usual question that are posed to the supporters of epistemic view. And if the state represents a knowledge that there are always these two questions, I think Mary was formulate this in a paper like knowledge about what and whose knowledge. And so there are basically two types, and one would be something which you can apply to the fragments of quantum theory, namely that this is a knowledge about some true state of affair or state of reality. But just because we have Bell's theorem, I would say this, I mean, we should go beyond that. We have to find something else. And the second one that I know is from quantum realism, or something more operational. Right. This is a knowledge about future experiments, or my actions, and so on. So where would you place yourself?
Okay. So I'm certainly not proposing that the knowledge that quantum states represents should merely be knowledge about the outcomes of future experiments. So I do want quantum states to be representing knowledge of the reality pertaining to some particular system. But I agree, it can't be reality in the sense of there's a variable there that has some value and I don't know what that value is. Because that would be to endorse this classical framework of causal model. And if you also want to be Leibnizian, which I do, you know that can't work because of Bell's theorem. But ultimately, when I ask what's at stake concerning being a scientific realist, I don't think I'm committed to positing variables that have different values. Like, to my mind, what's important in a realist interpretation is having a causal account of what's going on. Now, does that causal account have to have the form of, at every moment in time, every things are fixed by the value of certain variables and that evolve? No, not necessarily. I think there's room for causal accounts that don't make that assumption. So I don't know what so I should say that in the second half of my talk I said, hey, the formalism of quantum mechanics perhaps can be recast as a calculus for manipulating your incomplete knowledge. But I did not say what that knowledge was knowledge about. All I said was that, for example, the variables that act as common causes, they can't be variables that take on some value. They have to be something more exotic. And so I don't know the answer, but I would expect that ultimately the knowledge is going to be about causal structure, and whatever part of causal structure remains, it's not going to involve variables taking definite values, but I think there could still be enough structure left there such that our states of knowledge could be knowledge about that. So it's kind of a vague answer. I don't know.
Causal structure should be objective.
Yes.
So
right.
But if there is a state of knowledge...
If we have a state of knowledge of something objective, that's totally fine.
But we never have a situation... But how I understood, there is no situation in which you would, by measurement, find out one or the other causal structure mimicking simulating what we have in a single event quantum, single event where we cannot assign a definite value before the measurement. I thought that your opinion is that the causal structure of this objective, which will not be no quantum uncertainty about that, because it is not represented itself through a state. And now I cannot combine of this use.
So maybe I was didn't use terminology correctly, but earlier we were talking about how the things that are ontological in these models are not just a DAG, but also a set of parameters. So if I have a classical causal model, every variable has some set of other variables that influence it, and there's some function, which I write down as a polynomial of this variable in terms of those variables, and the scalars that appear in that polynomial are a description of some fact about the causal model. That is a fact that doesn't get represented in the DAG, gets represented by these real numbers in the parameters. So it can be the case that you have ignorance of those values, for example. So there's ways of being ignorant of the causal structure while still being ignorant of the causal model while still being certain of the overall structure of the model. But remember from the example we had earlier that these two things become intertwined in a way that I can be certain that the overall causal structure is this, but because I don't know the parameters, maybe I don't know whether it's this one that's acting non-trivially or this one that's acting non-trivially. So there still could even be some sort of uncertainty about sort of where the non-trivial actions are, even though there's certainty about all the places where there could be non-trivial actions.
Other questions, comments, constructive critiques?
Linked to the previous question, the knowledge of reality is situated probably at the us. So somebody who is
right. Whose knowledge? Whose knowledge?
And we have the issue of influencing by observing
right.
what happens. So how is this? How can you? How do you distinguish actually? It was not clear for me. How do you really distinguish between this description of reality and description of the knowledge of reality when actually we somehow influence it? Or do we not influence? In the previous talk, there was this big question about the observer and a big question for Wigner and so on. But I didn't see how it crystallizes here. Or does it not matter in what you?
So there's definitely in this approach nothing of the flavor of it's my becoming aware. It's important that some conscious observer become aware of whether the cat is alive or dead before the cat actually itself is alive or dead, right? So there's these ideas that unless there's some conscious observer, the wave function doesn't collapse, and then when the conscious observer gets involved, the wave function collapses. So when I look at those kinds of descriptions of those types of interpretations, I diagnose the problem as people thought of that entangled state between the spin and the apparatus and the observer as a funny way of being for those objects. And it goes into this bizarre thing with holistic properties that's neither alive or dead. And so something needs to come along and make it have well-defined properties. And I say, the mistake was the category mistake of thinking that a quantum state represents reality. And think about this quantum state represents some anomalous way of the cat being. No, it just represents a particular way of knowing about the physical state of the cat. And nothing anomalous about the cat state itself. And so in that sense, I have no need to, so there's none of that. But in terms of, is it the case that the physical process of acquiring information about something sometimes has a back action? Yes. So in all the experiments I talked about here, I learn about system B by acting on system A. And because they're space-like separated, in the solutions I endorse, there's no causal action of my observations here on that system over there. So that would be an example where I update my knowledge about that system without influencing it at all. It's just doing whatever. Physically, its physical state hasn't changed after I've done my measurements. So there's no question of causal influence. I'm just refining my uncertainty in one of many ways, depending on what I've chosen to measure here. But in other situations, like the ones that's pertinent for the projection postulate, if I have a system and I do a measurement and I ask what's the quantum state of the system after the measurement, then when you analyze in this sort of approach the projection postulate, it involves two components. There's a Bayesian updating component, but there's also a disturbance component. So if I take the particle that I want to observe, and the way I do it is I couple it by a von Neumann coupling to some probe particle, then in these sorts of approaches, I necessarily have ignorance about the probe particle, and there's an action-reaction principle, so my ignorance of the probe particle infects the system. So I might resolve my uncertainty about one property of the system, but I inject uncertainty into the complementary property. So I actually will modify the properties of the system in a way that depends on the initial properties of the probe. I have a lack of information about those initial properties of the probe, so I have a lack of information about the final properties of the system that was monitoring. So in that sense, measurements induce disturbances, yes.
But I'm still able to reproduce it in a way that I can still make statistics.
Yes. How does it work?
How do they say that this is I reproduce it in the same way so that I can have some statistical information in order to generate some correlations? How do I know that this is identical in some sense, or do I postulate identity?
So I'm not going to follow that, but maybe it would help if I went through.
Normally I have to reproduce something in order to be sure that it works. Yeah. So the statistic that you mentioned coming from medicine and so, they imagine that they can reproduce the same thing, and
right.
We have now a problem of, do we have a problem of reproduction or not?
No, in the sense that, all the cases I'm talking about are ensembles of systems. So when I say that quantum mechanics predicts this relative frequency of outcomes, what we're imagining is that we've set up the apparatus and then repeated the experiment many times and calculated statistics. And everything I've been saying has that in mind as well. We have an ensemble of repetitions of the experiment, and what the quantum state represents is statistical properties of that ensemble. But a statistical property of an ensemble is also a property of my epistemic state of a single thing drawn from the ensemble, right? So if I have like a vat that has black and white balls in it, and I tell you the relative number of black and white balls is, 75%, you can say that's a physical property of that ensemble of balls. But I can also say that, when somebody's drawn a single ball and asks me, what do I predict about whether it's going to be black or white, now that number represents my epistemic uncertainty about the color of that individual ball. So it's the same thing here, right? And I want to say quantum states, they represent properties of ensembles of systems, equivalently properties of agents' knowledge of a single system. I consider those as equivalent things.
Just very briefly, kind of guess, if you were to hedge your bets, and if you think there are these onto states, should it be a goal in physics to try and have a theory of those? In the sense of, should we try to continue with sort of on this quantum mechanical path, which is not the right kind of thing to describe all these kinds of things, or should we try and actively look for a new theory that describes what the world is really like?
I mean, certainly, yeah, everything I've said here presumes that you can make this distinction between the ontology and what we know about it. And I certainly think that we need a theory of the ontology, and it's just that a lot of the formulas in quantum theory are not formulas about that ontology, but they have more the status of Bayes' theorem, right? So if I look at Bayes' theorem, perfectly well-defined formula. Is it like Newton's law? No, Bayes' theorem is not like Newton's law. Newton's law is a description of an ontological dynamic. Bayes' theorem is a normative rule for how you ought to make bets so as not to lose money, and for how to survive in the world. In the face of incomplete information, if you want to survive in the world, you're better off using Bayes' theorem. So Bayes' theorem is useful. Newton's law is useful. If somebody goes around using Bayes' theorem, nobody asks them, aren't you uncomfortable that you're using this formula that doesn't describe reality? And they might say, well, I recognize it doesn't describe reality. I'm using it in this way, and I would love to have more things like Newton's law that will help me describe reality as well. And I'll keep using Bayes' theorem, and I'll couple it to Newton's law when I have uncertainty about the Newtonian state, for example. And so the idea here is that a lot of the formulas of quantum theory are not like Newton's law. They're like Bayes' theorem. But there are going to be other formulas that are like Newton's law. So I think when I say a system undergoes a unitary dynamics, from this point of view, that unitary dynamics, say, from the past to the future, is like the functional dependence in a classical causal model. It's ontological. It describes how the future state depends on the past state. But, like we said over here, that there's an isomorphism between maps on the ontic states and maps on the epistemic states. So in a sense, unitaries, encode the space of ontic dynamics and the space of ways in which my knowledge can change. But there ought to be a description of the reality underneath the quantum formalism, some way of describing reality alone. It ought to evolve in a way that's isomorphic to unitary evolution. And we ought to be able to understand how quantum states can be states of knowledge of that reality. So ultimately, I hope that I could have an interpretation where it's like, these are the formulas that describe reality. And now you, as an agent in the world who's trying to learn about reality, ought to use these formulas to survive in the world and reason about that reality. So yeah, I think ultimately we should have such a thing.
Okay, I think it's a good moment to stop here. Thank you again for coming, and let's thank our speaker once more.